In the last few lectures, we discussed about context-free grammars and the family of languages represented by them, namely context-free languages. We have seen some normal forms for context-free grammars, namely Chomsky normal form and Grayback normal forms. Also, we have seen when a context-free grammar is known as an ambiguous grammar, which is defined in terms of leftmost derivations or equivalently parsed trees. And the agenda for the next few lectures is to discuss about a class of automata representing context-free languages or context-free grammars. Today we are going to start discussing about the class of automata, namely push down automata representing context-free languages. Before we see what is a push down automaton, let us recollect the basic structure of a finite state automaton and also recollect the way a finite state automaton executes. If you recall, this is the basic structural units in a finite state automaton. There is a control unit with finitely many states. Given this figure, the current state is S, and a read head pointing to one of the input cell, which can read the next input symbol. And what is a transition? Read the current input symbol, which is A, then also look at the current state, and based on the current state and the current input symbol, change the state. That is a move or transition in a finite state automaton. And in addition to this, as a part of the transition or move, the read head will be positioned to the next symbol. Okay, so the transition is depending on the current state and current input symbol, and the transition defines the next state, and if there is no state change, the next state can be defined as S itself, and at every step the read head needs to be positioned to the next symbol. So, if you apply this transition, the new configuration can be represented by this figure. The read head is pointing to the next symbol, the state is changed to P. And an input string like this is accepted if after processing that input string from the start state, the automaton must be in a final state. So, that is the acceptance criteria. So, at the end, after processing the input symbols, the automaton needs to be in a final state. Now, we can see what is the structure of a push down automaton. So, in addition to the structural components in a finite state automaton, one additional structural unit is getting added, which is a stack, which can be used as an intermediate storage. It is a last in first out data structure, and which can be used as an intermediate storage. So, when compared to a finite state automaton, here the automaton is having memory, of infinite capacity. The stack is not bounded theoretically. And what is a transition? A transition needs to read the current input simple, in this case small a, and the current simple on the top of stack, which is capital X. Okay, so a transition will be characterized by the current state S, the current input simple small a, and the current top of stack simple, now in this case capital X. And then the transition defines what is the next state, and also a string of stack simples which will replace the top of stack simple capital X. Here an important thing to notice is that at every step or transition, a push down automaton will take out the top of stack simple and will push in the string which is defined as a part of the transition. And how is it pushing in? Yk will go as the simple, or Yk will go first, just like pushing this string from the left into a cylinder. You can think about it like that to remember which one will go first. You think of pushing this string with a stick and assume that here there is a well or a cylinder to which it is going down. So in addition to this, as in the case of a finite state automaton, the read head needs to be positioned to the next simple. That's what I am saying. So if you apply this transition on this state of the automaton, what will happen? The state will be changed to P, the read head will be positioned to B, and this X will be popped out and this string will be pushed in where Yk will go first. That is what is shown here. So this is basically a step or a move or a transition in a push down automaton. So when compared to the finite state automaton, in the LHS of the transition function definition, one more component is there. It's not only the current state and the current input simple, but also is depending on the current simple on the top of stack. And what is the RHS? In case of finite state automaton, just the state, next state. Here it is the next state and also which string is going to replace the top of stack symbol. Remember, always the top of stack symbol is going to be removed. If you want to retain it, you can say X here. Okay. Now we can see what is an accepted condition for a push down automaton. Recall, for a finite state automaton, the acceptance criterion is that when you finish reading input, the automaton needs to be in a final state. If it is so, accepted, otherwise rejected. Here you can see two different acceptance criterions. One is this: if you start processing where the read head is pointing to the first simple of the input with the stack containing only the bottom simple, this is a special simple on the stack called the bottom simple, and it is just used to mark the bottom of the stack. So this is how a push down automaton can start, and this acceptance criterion needs to empty the stack when you finish reading your input. It doesn't matter in which state you are in. So the final or non-final states are not there in this criterion. It just checks when you finish reading input, the stack is empty. If it is empty, the string is said to be accepted. And this criterion is called stack empty acceptance criteria. That is, when you finish reading the input, if the stack is empty, input is accepted, otherwise input is not accepted. And see that even the bottom of stack symbol needs to be taken out. So this is the first acceptance criterion. One more is there, just like the finite state automaton. Here if you start with a state S, start state, read head pointing to the first symbol and only bottom of symbol on the stack. When you finish reading input, you need to be in a final state. So this is the final state acceptance criteria. In that case, the stack content is immaterial. That is not considered for this criteria. So this is the final state acceptance, very similar to final state automaton. When you finish reading your input, if you are in a final state, the input is accepted regardless of what content is there on the stack. So these are the two acceptance criteria: stack empty acceptance and final state acceptance. And in a lecture later, we shall prove that they are equivalent. Now no need to worry about it, we will see later. For us, now there are two criteria. Now we can try to have a push down automaton for this language, which is known to be a non-regular language and known to be a context free language. We have seen a context free grammar. Now we can see how we can get a push down automaton. Suppose you give the input AQ, BQ, it is in the language, and this is the starting configuration or status, start state, read here to the first symbol and only bottom of stack symbol. And let us say we want to accept by stack empty condition, that is, we want to finish reading and we want to empty the stack. Empty the stack if and only if the input is in the language. How we can do it? What is the idea? Not difficult. So what you can do is, you want to count the number of A's and number of B's and you want to see that the counts are same. You can try to use the stack to count the number of A's. What you can do is, for every A you see here, you push a symbol onto the stack, say capital X. And no need to change state, you just count the number of A's. So when you finish reading the A part, 3 A's are there, you will be having 3 symbols on the stack, whatever that symbol is. Let us fix it as capital X. If you want, you can say capital A, it doesn't matter. So this tells you that there are how many? 3 A's which are processed. Now what you can do is, you can start reading a simple B, and whenever you read a simple B, you can take out an X. So you just take out, no need to push anything onto the stack. So if you do that, do it in a new state. So finally after you finish reading input, all the 3 X's will be taken out, and at last you take out the bottom of stack symbol also. This is what you can do. So we can see how can we get transitions. So what will be the first transition? You are in the start state, you are reading a small a and only the bottom of stack symbol on the stack. So what you have to do? You have to push a symbol on to the top of the bottom symbol. So what you do, you know that both will be taken out, so you have to put it back, and also you have to put a capital X is what we have seen. So without changing the state, what you do, replace the bottom simple with X bottom, and if you apply this transition, you will get this. You read out that simple, read head is pointing to the next simple, and you just pushed one more simple, a capital X, meaning one A is processed. Now see what is the transition that you need. You are in the state S, you are reading a simple small a, and capital X is the top of stack simple. The transition is not defined. Can you tell me what transition you need? What is the RHS, that pair? You need not change the state, but you want to get one more X on the top of stack. You know that this X will be taken out, so you can say replace that with 2 X's. And if you apply this transition over here, this is what is happening. Read head is moving to the right, you are getting one more X. And now see, you are in the state S, reading small a, and capital X is on top of the stack, and you already have a transition defined, just fire it. What will happen? An X will come in the top, this will move over here, and that's it. Now you have a situation where you don't have a transition for this. The state is S, input is small b, top of stack simple is capital X. So what we can do? Here you realize that I finished reading the A part. So now I got a B. So after that I should not read any A. So for doing that, to prevent reading A's, you have to change your state. Maybe you change it to some other state P. And what you can do with this, with the stack, because now you are reading a B, you can take out an X, because it is like cancelling the last occurrence of A, you can take out. So the transition required is change your state and don't push any more simple. Anyway you are popping it, so if you are not pushing anything, this is how you can represent it. So if you fire that transition, this is what is happening. Read head is pointing to the next simple, and now the case is undefined. You have P as the state, small b as the next input simple, and X as the top of stack simple. So what you need? No need to change the state, but take out that X as well. Okay, if you fire that, this is what is happening. Now you can see that PBX, there is already a transition. You apply that. You will remain in the state P, and you move out of the input tape, and this X is taken out. Now see, this is what you have. P current state, nothing is there on the tape, and bottom of stack simple, meaning you just processed n number of A's followed by n number of P's. That is why you finished all the X's in the stack. So what you did is you read a string which needs to be in the language. So you know that you have to empty the stack, you just take out. Remain in P, you take out this simple as well. So this is what you are getting by the acceptance criterion you are accepting. Are we done? Not exactly. Ask this question: how the PDA can accept null string? When you substitute n as 0, the resulting string is null string which is in the language, and for that this is the configuration of status. Nothing is there on the input tape. S is the simple, sorry, start state, and you have this bottom of stack simple on the stack. So what you do? You don't have a simple, and bottom of stack is there, so you can just take out and remain in S. That means if you fire this, you are emptying the stack, you finished up the input, and you can accept. So you need this transition as well. So this is what we obtain as the sequence of transitions, or sorry, set of transitions in the automaton, and maybe you can verify the working of this automaton on these input strings and do it as a homework exercise to understand how this automaton works. And now with this example we can try to formally define what is the structure of a push down automaton. Let us utilize that example to identify the components required in a push down automaton. And you can define a push down automaton A as a septuple. 7 elements are there, where what is Q? Q is the finite set of states, same as that of a finite state automaton. Finite set of states, here S and P. And then sigma is the input alphabets, here small a and small b. And capital gamma is the finite set of stack alphabets. If you recall from the previous example, capital X and bottom of stack simple. And what is next? Small s, which is an element of the state set called the start state, just like in the case of finite state automaton. Next is transition function. This is how you can formally represent it. What is it saying? From the current state for the next input simple like this, or it could be epsilon, and for the top of stack simple, here it is capital X, here it is bot. You say what is the next state, and you also say what is the string of stack alphabets going to replace this stack alphabet. You can easily observe that it is a correct structural definition of that relation. And you can see that it could be non-deterministic. Suppose the next input simple is A and you are in the state S, you can apply any of these transitions, non-deterministically select. So by definition what we are defining is a non-deterministic push down automaton. And the next is bot, which is a unique simple on the stack alphabet known as the bottom of stack simple. The purpose is clear from the example. And at last you have a subset of states designated as final states. Not that only for one acceptance criterion you need set of final states. So this is how you can formally define a non-deterministic push down automaton. And the structure of the transition relation makes it non-deterministic. Now we can look at another example. Try to get a push down automaton for the set of all strings over AB with equal number of A's and B's. This is not to be a context free language because we had a context free grammar, and also proved to be a non-regular language. So here we can use the stack to remember the number of A's and B's. Okay, you can do it in a smart way. Suppose you are in the start state, then you know that you have to accept epsilon, and this is the transition to accept epsilon. And what you do, see, you need a final state acceptance. This is the other criterion that we are applying. That means you just take out even the bottom of stack symbol, jump into the final state. So you will be accepting. At the same time you are emptying the stack even if that is not required. Now suppose you start with a small a, then what you do? You have to remember the number of A's. The same trick, you are remembering it using a capital X. Now suppose you get an A when capital X is on the top of stack, then you need to put one more X, and that is what you are doing. Not difficult to get these transitions. And now this is a more interesting case. Suppose you are getting a B while X is on the top of stack. what you can do? So you know that this x is representing a small a. So what you can do is you can just take out, you can take out, right, because you just want to make sure that number of a's and b's are same. So previously there was an a, you cancelled that occurrence with this occurrence of b. That is what you did. Now look at this case. Suppose you start with a b, the first simple is a b, then you have to remember that number of b's using another variable, say capital Y. So just like x, y is going to remember b's. Now suppose you are getting a b while you have capital Y on the top of stack. No doubt you have to push one more b, or the symbol representing b. That's what you are doing here. Now suppose you get this situation, that is you are getting an a while you have capital Y as the top of stack symbol, just like what you did here. That means previously there was a small b, now you are getting a small a. You can cancel them by taking out that y. That is what I do. Just 7 transitions, and you can verify that this is a correct design, and see what happens on the computations on these strings. Okay, you verify that in every case, if the string is in the language, it is accepted, otherwise it is not accepted. Okay, and you can also try with some strings not in the language. And now I am moving to the last slide, where I am giving you an exercise problem for you to practice how, not one exercise problem, 3 exercise problems to decide push down automaton. Acceptance criterion, you can decide whether you need empty stack or a final state. With this, we are finishing this lecture. Today we started discussing about a class of automata, namely push down automaton, representing context free grammars, and we saw that when compared to a finite state automaton, the only structural difference is an addition of a structural unit, which is a stack as an intermediate storage, which you can utilize to remember required information about the string read so far, to the extent that you can use stack to remember data. With this we are finishing. Thank you.